We're continuing with section 15.1, working with logarithmic functions. So here we're working with log base 1/2. So, and finding some values of the exponents for that. So in the first one here, log base 1/2 of 4 is equal to y. So circle the wagon, 1/2 to the y is equal to 4. Well, 4 is the same thing as 2 squared, which is the same thing as 1/2 to the -2 power. Remember, negative exponents are going to take the reciprocal of our base. So that means our y is equal to -2. Next one, we've got log base 1/2 of 1/32 is equal to y. Circle the wagon, 1/2 to the y is equal to 1/32. 32 is the same thing as 2 to the 5th. So 1/2 to the 5th is the same thing as 1/2 to the 5th, which means that y this time is 5. And then we've got log base 1/2 of 2√2 is equal to y. Circle the wagon, 1/2 to the y is 2√2. So we want to change this into exponential form. So you've got 2 to the 1 times 2 to the 1/2. So we want to add those exponents. We end up with 2 to the 3/2. So 2 to the 3/2 is 1/2 to the -3/2. So that means y will be equal to -3/2. So here we're dealing with log base 7. So we're going to have log base 7 of 343 is equal to y. Circle the wagon, 7 to the y is 343. You can check on your calculator, you'll find that y is equal to 3. Log base 7 of 1/49 is equal to y. So 7 to the y is equal to 1/49. And here y is going to be -2. And then we've got log base 7 of √7 is equal to y. So 7 to the y is equal to √7. Remember, √7 is the same thing as 7 to the 1/2, which means that y is just 1/2. You can use a scientific calculator to find the logarithm of any positive number x when the logarithm's base is either 10 or e. These work for a base of either 10 or e. When the base is 10, you are finding what is called the common logarithm of x, and you use the calculator's log key because log base 10 of x is also written as log x, where the base is understood to be 10. When the base is e, you are finding what's called the natural logarithm of x, and you use the calculator's ln key, ln for natural log, because log base e of x is also written as ln of x. So all we're doing right now is plugging some values into your calculator, seeing what the output is. They're having you double check the result by circling the wagon and figuring it out, but the calculator knows what it's doing. We're going to trust that it's doing it correctly. First, we want to find the common logarithm of 0.42. So we grab our calculator. Common logarithm is the standard log. So we take log of 0.42, which is we want the 1,000th place, so that's 3 decimal places, so -0.377. Oops, dropped my pen. So log of 0.42 is -0.377. And then we can also take the natural logarithm of 0.42 by taking ln of 0.42, which is -0.868. So we want to find the common logarithm and the natural logarithm of these numbers. So if we take log of 0.25 and then natural log of 0.25, I'm going to see what values we get. So log 0.25, we -0.602, and natural log of 0.25 is -1.386. So we have -0.602. and then -1.386. Log of 4 and natural log of 4. Let's see what we get with those. So log of 4 would be 0.602, and natural log of 4 would be 1.386. So you'll notice these values are the same, just one's positive and one's negative. Because if we think about what it means, to do these, if you tried to circle the wagon again, you'd see because of the bases, raising them to a fractional exponent versus a whole number exponent is what's getting us the positive and negative values there. So we can do some modeling with logs. Standard scientific formulas that involve logarithms, such as the formulas for the acidity or pH level of a liquid and the intensity level of sound. It's also possible to develop your own models using logarithms by finding the inverses of exponential growth and decay models. So this first example works through a pH problem, finding the pH here in a swimming pool. We're going to work through this one though. We've got some type of bacteria used to turn milk into yogurt. The population of a colony of 3,500 bacteria at time t can be modeled by the function p of t is equal to 3,500 times 2 to the t over 73. How long does it take the population to reach 1,792,000? So we're solving our logarithm for t. So first thing we're going to do is divide both sides by 3,500. And then we're actually going to take, we're going to rewrite it in log form. So log base 2 of p over 3,500, is t over 73. We essentially took the log base 2 of both sides of the equation to get rid of, remember log is an inverse. So an inverse of raising 2 to a power would be to take log base 2 of that power. It's like taking the inverse of x squared is the square root. So the inverse of 2 to the x is log base 2. So take the log of both sides to undo taking the 2 to the power. Now we multiply both sides by 73 to get t by itself. So then they plugged in the value for p, which is 1,792,000. Doing that division, we get 512. So 73 times log base 2 of 512. Log base 2 of 512, that's the hard part here. We're going to have to actually solve that out. So we'd say log base 2 of 512 is equal to y. So circling the wagon, 2 to the y is equal to 512. You can figure out what that power is. It ends up being 9. So log base 2 of 512 is 9. We'll plug that in. 73 times 9 would be 657, it looks like. So in 657 minutes, the colony reaches that population, and that's about then 7 hours. Sorry, 11 hours. Ooh, 11 hours. The intensity level in decibels of sound is given by the given formula, where I is the intensity of the sound and I sub 0 is the intensity of the softest audible sound. So what's the intensity level of a rock concert if the sound has an intensity of 3.2? So we're looking for the intensity level of the concert. So we'll use L is equal to 10 log base I. Sorry, log of our I, which is 3.2, over I sub 0, which is 10 to the negative 2. So we can plug that into our calculator. 10 times log of 3.2 divided by 10 to the negative 12. Close it off. The intensity level is about 125.05 decibels. The mass in milligrams of beryllium-11, a radioactive isotope, in a 500 milligram sample at time t is given by the function. When will there be 90 milligrams remaining? So essentially, we know the ending value, 90. We're trying to figure out for what time does that happen. So essentially, we're going to, at this point, divide by 500. We want to get that e by itself, because once that e is by itself, to undo that, we can take the natural log. So natural log both sides, that ends up being 0.18, and then you'll just be left with the exponent. Solving for t, we get natural log of 0.18 divided by negative 0.05, and it's about 34.3 seconds.